the last topic of this section is to talk about growth rate of functions. Of course, now the growth rate means growth, right? So therefore, we are interested in the functions that are growing. We want to compare which one grows faster. So therefore, we are assuming that the function are always increasing, they're growing. So this has to be true. Limits of x approaching infinity of f of x and g of x, they're both approaching infinity. Now we say if f, when f is grows, when f grows faster, then this is true. So one of these two is true, right? So you know this grows faster. That means it's getting larger, larger and larger quicker than the g of x, right? So therefore, when you compare these two, this is f will be much larger. This is less larger, okay, less larger. Therefore, when this happens, you know, much larger will dominate the less larger one. So eventually, the bottom is getting much more, much larger than the top one. So therefore, the limits must be zero. Okay, the limits must be zero. So in other words, put it in another way, if you see that the limits of two functions when x is approaching infinity, if you see the limit is zero, that means this must be much larger than the top one. Otherwise, it won't be zero. So then you can decide f must grow faster than g. This is equivalently, if you see that the f over g, this ratio is approaching infinity, in what scenario you'll get a result that's infinity? It can happen only when the top, the numerator, is much larger, right? Much larger than the bottom. So when this happens, you know the top one is growing faster than the bottom one. I do not advise you to memorize these results. I advise you use the logical thinking to make this, to remember it. Don't just mechanically memorize these results. Well, sometimes the ratio of these two can be a constant. In this case, we say they are comparable. We are not going to say one is growing faster than the other. When we say f grows faster, that means significantly. Okay, it dominates the growth. Now, let me give you one quick example for this third scenario. For instance, think about 2x, right? This is growing to infinity when x is approaching infinity. And 3x is also growing to infinity when x is approaching infinity. But this ratio is approaching two-thirds when x is approaching infinity. And therefore, this is constant. We call they're both growing, but their growth linearly. They're comparable. None of the, we cannot say one is growing much faster than the other one. They're both linearly, even though the bottom one actually grows faster than the top one, right? But we don't call them significantly. So that's the little discussion foundation to introduce the definition. So let's work on the problem here. So natural log of x square and then square root of x, which one grows faster? How do we look at that? You need to compare the rate. So can do that, just look at the ratio. Can you do square root of x over natural log of x square? Yes, you can, just both will work, okay? You just need to interpret the result correctly. So now look at the limits x approaches infinity. It's already known that both are approaching infinity, infinity over infinity. So we use the L'Hopital's rule to find these limits. So let's do that. I'm just working on the first one, okay? I'm not going to work on that one. You can try that one. Absolutely suggest you to try that. Derivative of the top is, you use chain rule, u square. So you have 2u. U is your natural log of x, times derivative of u, which is 1 over x. And the bottom one, square root of x, the derivative is 1/2, x to the power negative half, right? X to the power negative 1/2. Okay, and then you're going to simplify. So this is going to be, you see a constant 4. I'm going to move that out. limit x approaches infinity, and here I have natural log of x. And then if you simplify, the 1 over x, you can move it down to the bottom. Actually, it becomes x to the 1/2 if you combine the powers. Now, if you plug infinities, you still have infinity over infinity, infinity over infinity. So therefore, you apply the L'Hopital's rule one more time. You get 4 times natural log, limit x approaches infinity, the natural log of x, the derivative is 1 over x. And the derivative of x raised to power 1/2 is 1/2. Basically, 1/2 times x to the power negative 1/2, right? And if you simplify, this is equal to, I need a little more room here. This is equal to 8 times limit x approaches infinity. Where's the 8 from? It's coming from 1/2. On the bottom, it becomes 2, and then times 4. Now, when you simplify that, you get 1 over x raised to power 1/2. When x is approaching infinity, this guy is approaching 0. Okay, so when this happens, you do know that, okay, that means the bottom has to be much larger than the top, right? This has to be much larger than the top. So therefore, I do know that square root of x must be much larger, which means grows faster than natural log of x squared. So this is the symbol that we will use to represent square root of x grows faster than the natural log of x squared. I would like to now I would like to point out to this result. This is the theorem that follows these examples. Do you see that p and q, there are any real numbers? So power function x to power p always grows faster than the natural log raised to any power. So in other words, if I ask you which one grows faster, x raised to 0.0001 versus natural log x raised to, say, 1 million, say 1,000. Well, I cannot write 1 million, 1 million, there are too many zeros. But say a huge power. Eventually, when x is big enough, this guy will always be larger than this guy. Okay, so that's the first result.